For years, the hunt for extraterrestrial intelligence involved probing the heavens for weak radio signals. But then came the arrival of an entity dubbed Oumuamua, which decelerated while hurtling into our solar neighborhood. According to formal documentation, its increasing luminosity ought to follow basic physical principles. Yet, over a mere 4 weeks, its radiance spiked 5-fold beyond predictions. At the same time, spectral analyses detect metallic signatures typically produced in artificial processes, not occurring naturally. Moreover, defying typical comet trajectories, this interloper shows almost no deviation from its path, even as it emits detectable gases. Should Oumuamua prove to be a natural phenomenon, none of these traits make sense. If artificial, it could mark humanity's initial encounter with a probe guided by extraterrestrial minds. What secrets lurk within these baffling indicators? Generations of radio observatories have combed the cosmos for any engineered emission. A signal, a murmur, perhaps an encoded summons from distant realms. Yet amid the quiet, a different avenue has emerged. Occasionally, a tangible entity bridges the vast interstellar void and penetrates our star system. If macroscopic technological artifacts exist anywhere, they might manifest precisely like this. Not as transmissions, but as solid intruders. From the beginnings of contemporary stargazing, just 3 such intruders have been verified. The probabilities are immense. Out of every 100 billion solar-orbiting comets, only 1 or 2 originate from beyond our system. Every such incursion represents a stellar windfall, an opportunity to examine something constructed rather than formed by nature. Conventional SETI, emphasizing radio waves and laser pulses, presumes advanced societies transmit actively. But suppose the most compelling proof arrives in tangible form, quiet, motionless, tumbling through the void? Physical relics can retain data, machinery, and even purpose eons after their creators vanish. In contrast to ephemeral broadcasts, sizable relics persist. They invite examination, quantification, and, with fortunate timing, direct encounter. The infrequency of interstellar wanderers elevates each sighting to an international spectacle. Oumuamua in 2017, Borisov in 2019, and now 3I/Atlas. Every instance offers a unique glimpse, a relic from an era and locale we might never revisit. Their exceptional scarcity implies that a lone irregularity holds profound significance. The cosmos grants scant do-overs. SETI's foundational concepts were molded by the instruments of its time: parabolic antennas, data analyzers, hunts for anomalies amid static. Yet, Oumuamua's unveiling transformed the strategy. Abruptly, the quest for techno-signatures encompassed not only auditory cues, but also transient passers-by. 3I/Atlas transcends the category of ordinary comets. It embodies proof in motion, a courier from a foreign stellar realm, and potentially, if we scrutinize it with sufficient care, confirmation that solitude is an illusion. On May 7, 2025, NASA's Transiting Exoplanets Survey satellite, TESS, captured a dim, swift traveler amid the dense stellar backdrop near the Milky Way's core. Initially, no notifications sounded. The trace drowned in a vast archive of cosmic debris, its path too faint for routine detection algorithms, its sheen obscured by myriad foreground lights. For almost a month, the visitor glided forward, recorded repeatedly in TESS's wide-field snapshots. Layer by layer, each frame accumulated subtle imprints on storage systems. It took until July 1 for the Atlas survey, operating from its station in Rio Hurtado, Chile, to highlight the irregularity. The entity had intensified dramatically, multiplying its output by 5 since TESS's initial glimpse. Still, its location clung to the galaxy's teeming disk, a zone infamous for concealing fleeting phenomena. The Minor Planet Center registered the report, and soon global telescopes redirected efforts to track it. In the ensuing period, researchers delved into historical datasets. The Zwicky Transient Facility and Pan-STARRS uncovered prior sightings from late June. Their logs depicted the object's consistent arc across the celestial dome. Hobbyists pitched in, poring over open repositories, their contributions bridging voids from June 14 to month's end. Each additional data point sharpened the brightness profile. exposing an escalation that surpassed straightforward orbital mechanics. The challenge stemmed from the heavens themselves. Originating from Sagittarius, the intruder's vector confounded even premier monitors, blending its output with ambient glows. Only post-July did the extent of its preliminary behavior crystallize, aided by exhaustive dives into petabytes of past records. For the TESS and Atlas crews, the find unfolded not as an abrupt flash but a gradual ignition, kindled weeks prior to recognition of an extrasolar guest. From May 7th to June 3rd, 3I/Atlas amplified its light by a factor of 5, a rise that upends norms for remote icy bodies. Conventional models forecast a tame uptick, perhaps 1.5-fold, as it transitions from 6.36 to $5.46 from Sol. Photometric readings from TESS, ZTF, and Atlas, however, document a consistent 5-fold climb, unwavering over $0.9 of its journey. Calibrations across instruments aligned seamlessly, verified against local suns and modeled stellar twins. Variations in the light output, systematic and below 0.1 magnitude, persist without fading. This pattern shows no signs of a temporary surge or equipment glitch. By combining data from daily image stacks and offset exposures, the brightness profile forms a distinct upward curve, steadily climbing despite the object's passage through the dense star fields of the galactic center. Positioned at $6.36, such behavior remains unexpected. Water ice remains solid. Solar heating feels remote. Nevertheless, the surrounding haze is evident, and estimates of the dust's effective area surge from roughly 300 square kilometers in May to more than 1,700 by July. These figures withstand close examination, as uncertainty margins are narrow enough to dismiss noise from chance or stellar interference. When aggregating the brightness totals, explanations based solely on alignment become unlikely. The surplus illumination requires a rationale that aligns with both the schedule and the extent. No individual observation program, regardless of its sensitivity, fully captures the scale of the shift. The unfiltered observations offer scant space for doubt. 3I/LOS exhibited activity and stood out as unusual prior to its formal cataloging. Investigating solutions starts with the metrics. A brightness increase by a factor of 5, exceeding all projected alignments, calls for more than a quick review of the records. Researchers consider standard possibilities, device malfunctions, contamination from the backdrop, or a fortuitous view piercing the Milky Way's core. Each option undergoes rigorous testing, verification, and dismissal. The brightness profile remains consistent over various instruments and global sites. Its curve too gradual for coincidence and too premature for typical comet outbursts. Certain experts propose that the object's approach velocity might have been misjudged, obscured by the thick concentrations of stars in Sagittarius. However, even with adjustments for overcrowding and refreshed brightness calibrations, the additional glow endures. The measurements fail to align with a gradual natural process. This opens possibilities to more daring concepts. Might 3I/LOS have activated propulsion? A deliberate slowdown to synchronize with solar system orbits? Though this idea resides on the edges of convention, it matches the observations. An intentional velocity reduction, performed well beyond solar influence, could account for the ongoing early enhancement without invoking water, ice, or conventional outgassing materials. In that case, the emissions would signal purpose rather than chance. Still, each bold conjecture faces skeptical restraint. The cosmos often deceives vigilant watchers, and evidence must be compelling. As discussions evolve, focus moves to the composition of the haze, where another hint could lurk openly. High-resolution spectrometers at the VLT, sensitive to the subtlest emissions of elemental signatures, detected an anomaly in 3I/LOS's envelope. Prominent nickel features, sharp and distinct, emerged from the noise. In contrast, iron, expected to accompany it closely, showed no trace. Observers at Paranal devoted evenings to verifying setups, reapplying Turek adjustments, and comparing against reference spectra from labs. The results stood firm. Nickel appeared, iron vanished. No known solar system comet displays such a disparity. Typically, iron and nickel coexist, bound in remnants from stellar explosions and early planetesimal formation. The solar atmosphere itself contains around 18 iron atoms per nickel atom. Even in the grimiest, metal-laden comets, nickel seldom surpasses iron by over twofold. Here, the proportion exceeds 15, possibly reaching 50, with iron signals lost beneath sensitivity thresholds. Under Dr. Sofia Cardenas's guidance, the VLT team detailed the nickel transitions across standard and detailed spectral passes. Output estimates indicated about 4.6 grams of nickel per second at 2.85 Australian dollars, alongside strict caps on iron that pushed the nickel-to-iron ratio to extremes. Efforts to uncover concealed iron traces through image accumulation, searches for subtle overlaps, all yielded nothing. Conventional processes falter in accounting for this. Breakdown of nickel carbonyl, an unstable compound that sublimes easily at modest heats, might elevate nickel output, though iron variants prove harder to produce or endure. A few models invoke targeted erosion or unusual separation in protoplanetary origins. More audaciously, some invoke artificial remnants, like nickel-dominant superalloys worn down by long-forgotten drives, imprinting the envelope. To date, no fuel signatures or clear alloy markers appear in the spectrum, just isolated nickel and the absence of iron. The chemical balance tips unevenly, and efforts to find a mundane cause persist. By conventional measures, the orbit of 3I/Atlas presents an enigma. Position data from July to August reveal a deviation of only 1 to 1.5 kilometers per day, a mere perturbation, while the envelope and trail extend hundreds of thousands of kilometers astern. For inner solar system comets, sublimation functions as propulsion. Streams of gas deflect the core, yielding detectable deviations from pure gravity. Yet in this instance, the deviations hardly shift. The trajectory stays nearly gravitational. It treats the body like lifeless rock, ignoring the dynamic outbursts of gas and dust from an energetic comet. When the observations are piled together, this lack of propulsion influence becomes glaring. Borisov, the previous interstellar wanderer boasting a prominent coma, sailed past at roughly 100 kilometers daily, almost 2 full magnitudes faster. A simple tail ought to push the core along, yet 3I/Atlas defies it. Images reveal the anti-tail, the particulate haze, and prominent jets plainly. Still, its path holds firm without deviation. Simulations incorporating the documented material shedding and exposed surface forecast a far greater orbital deviation. The figures simply don't align. For an icy rocky pile to counteract this force so utterly, it would require immense density and bulk, enough to render even the most vigorous ejections negligible. However, brightness measurements and glow distribution analyses impose tight constraints on the core's dimensions. It's sizable, yet within believable bounds. Thus, the other possibility involves deliberate guidance, ongoing adjustments, precise balancing, or an enveloping layer that captures or reroutes the momentum. Nothing in nature fully bridges the divide between visible phenomena and recorded motion. With each positional refinement, the uncertainties narrow further. The overall shift clings to slightly over 1 kilometer per day, while under the level where cometary dynamics would demand more. The evidence is unequivocal. 3I/Atlas traverses the solar system as though shielded from its own emissions. The inconsistency isn't merely numerical, it's physical. Among typical celestial bodies, trajectories obey mass and impetus. Here, principles warp, and the route scarcely fluctuates. Among known extrasolar intruders, Borisov exemplifies the norm. Its enveloping haze and trail, laden with cyanogen and C2 molecules, followed a textbook curve across the inner realms. The data fit predictions perfectly. Non-gravitational pull registered around 10⁻⁻⁶ Wu per day, equating to about 100 kilometers of daily displacement. Each vapor burst prodded the nucleus. Every flare registered in the trajectory. Borisov acted as a proper comet, heeding the rules of evaporation and solar warmth. Oumuamua, however, ignored all standard protocols. No evident vapor release, no grains, no sheath. But its course swerved dramatically at closest solar approach, with an extra pull of roughly 2. 5 times 10 carat minus 4 AU per day. That amounts to 37,000 kilometers of total shift. All sans any jets or streamers to account for it. Its spin, a consistent 3 rotations daily, only amplified the enigma. Calculations stalled. Insufficient heft for an icy lump. Excessive motion for a barren boulder. Enter 3I/Atlas now, flipping the script entirely. The coma is unmistakable. The tail extends across hundreds of thousands of kilometers. And still, the detected motion hardly budges, merely 1-to-1. 5 kilometers per day. That's 100-fold below Borisov, a mere sliver compared to Oumuamua. The thrust impulse vanishes precisely when it should peak, emerges exactly where it ought to hide. 3 visitors, 3 behaviors, none sharing a common template. The cosmos, apparently, plays its enigmas in contrasting duos. The Vera-C, Rubin Observatory awaits on Cerro Pachón. Its 8.4-meter reflector, geared up, will scan the southern heavens every few nights. Through the Legacy Survey of Space and Time, LSSD, Rubin ushers in an age of prompt alerts. Its rhythm and acuity ensure the upcoming extrasolar guest, be it a comet or an oddity, won't evade detection amid the stellar throng. Notifications will fire off instantly, arming experts and hobbyists with a head start. Yet instruments by themselves miss the subtleties. The prior pair of intruders demonstrated this. When 3I/Atlas flared 5 times brighter against the Milky Way's core, it was dedicated enthusiasts who sifted gigabytes of stored imagery, piecing the initial reliable brightness profile. A cadre of volunteer observers, equipped with home rigs and free tools, bridged the intervals in professional scans. Their swift dispatches transformed fragmented shots into a coherent sequence, spotting bursts that might otherwise blend into static. Today, the urgency escalates. As Atlas nears the sun, no evening is wasted. Joint efforts, Rubin's routine patrols, Pan-STARRS in Hawaii, Atlas in Chile, plus enthusiast outposts spanning Pretoria to Perth, form a worldwide web. Every watcher contributes a reading, tightening tolerances, refining forecasts. The following surge or odd spectral signature might strike any time. Preliminary signals spread via Discord channels and Telegram chats, sparking ad hoc pursuits from scopes big and modest. The directive is straightforward. Watch the heavens, monitor the brightness, pursue the composition, exchange unprocessed shots and process composites. In this evolving pursuit, breakthroughs aren't elite territory. Each notice, each photo, each datum edges us nearer to grasping the extraordinary. A signal etched not in signals, but in trajectory, makeup, and radiance. Data from the Very Large Telescope's spectroscopy reveal nickel lines within the coma. There's a notable lack of iron, marking an atypical chemical profile, even as astrometric data show scant non-gravitational forces at play despite clear signs of outgassing. By comparison, 2 instances of I/Boris revealed standard cometary shifts, while 1I/Oumuamua exhibited marked deviations in its path with no trace of outgassing detected. These conflicting irregularities continue to elude explanation from prevailing models. Though no signs point to deliberate manipulation, the inconsistencies in Atlas's dynamics undermine conventional frameworks. Our strongest leads might emerge not via transmissions, but through extraterrestrial visitors whose trajectories outright defy our assumptions.